Cabin pressurization is used to create a safe and comfortable environment for aircraft passengers and crew flying at high altitude by pumping conditioned air into the cabin. This air is usually bled off from the engines at the compressor stage. The air is then cooled, humidified, mixed with recirculated air if necessary and distributed to the cabin by one or more environmental control systems. The cabin pressure is regulated by the outflow valve. Need for cabin pressurization. Pressurization becomes necessary at altitudes above 12,500 feet to 14,000 feet above sea level to protect crew and passengers from the risk of a number of physiological problems caused by the low outside air pressure above that altitude. It also serves to generally increase passenger comfort. The principal physiological problems are as follows: hypoxia. The lower partial pressure of oxygen at altitude reduces the alveolar oxygen tension in the lungs and subsequently in the brain, leading to sluggish thinking, dimmed vision, loss of consciousness, and ultimately death. In some individuals, particularly those with heart or lung disease, symptoms may begin as low as 5,000 feet, although most passengers can tolerate altitudes of 8,000 feet without ill effect. At this altitude, there is about 25% less oxygen than there is at sea level. Hypoxia may be addressed by the administration of supplemental oxygen either through an oxygen mask or through a nasal cannula. Without pressurization, sufficient oxygen can be delivered up to an altitude of about 40,000 feet. This is because a person who is used to living at sea level needs about 0.20 bar partial oxygen pressure to function normally, and that pressure can be maintained up to about 40,000 feet by increasing the mole fraction of oxygen in the air that is being breathed. At 40,000 feet the ambient air pressure falls to about 0.2 bar, and to maintain a minimum partial pressure of oxygen of 0.2 bar requires breathing 100% oxygen using an oxygen mask. Emergency oxygen supply masks in the passenger compartment of airliners do not need to be pressure demand masks because most flights stay below 40,000 feet. Above that altitude the partial pressure of oxygen will fall below 0.2 bar even at 100% oxygen, and some degree of cabin pressurization or rapid descent is essential to avoid the risk of hypoxia. Altitude sickness. Hyperventilation. The body unregistered trademark S most common response to hypoxia, does help to partially restore the partial pressure of oxygen in the blood, but it also causes carbon dioxide to outgas, raising the blood pH and inducing alkalosis. Passengers may experience fatigue, nausea, headaches, sleeplessness, and even pulmonary edema. These are the same symptoms that mountain climbers experience, but the limited duration of powered flight makes the development of pulmonary edema unlikely. Altitude sickness may be controlled by a full-pressure suit with helmet and faceplate, which completely envelops the body in a pressurized environment. This is impractical for commercial passengers. Decompression sickness. The low partial pressure of gases, principally nitrogen but including all other gases, may cause dissolved gases in the bloodstream to precipitate out, resulting in gas embolism or bubbles in the bloodstream. The mechanism is the same as for compressed air divers on ascent from depth. Symptoms may include the early symptoms of the tiredness, forgetfulness, headache, stroke, thrombosis, and subcutaneous itching but rarely the full symptoms of the bends. Decompression sickness may also be controlled by a full pressure suit as for altitude sickness. Barotrauma. As the aircraft climbs or descends, passengers may experience discomfort or acute pain as gases trapped within their bodies expand or contract. The most common problems occur where they're trapped in the middle ear or paranasal sinuses by a blocked eustachian tube or sinuses. Pain may also be experienced in the gastrointestinal tract or even the teeth. Usually these are not severe enough to cause actual trauma but can result in soreness in the ear that persists after the flight and can exacerbate or precipitate pre-existing medical conditions, such as pneumothorax. Pressurization of the cargo hold is also required to prevent damage to pressure-sensitive goods that might leak, expand, burst or be crushed on repressurization. Cabin altitude. The pressure inside the cabin is technically referred to as the equivalent effective cabin altitude or more commonly as the cabin altitude. The cabin altitude is the equivalent altitude having the same atmospheric pressure, so that if the cabin altitude were set to 0 then the pressure inside would be the pressure found at sea level. In practice, it is almost never kept at 0, in order to keep within the design limits of the fuselage and to manage landing at airfields higher than sea level. The cabin altitude of an aircraft planning to cruise at 40,000 ft is programmed to rise gradually from the altitude of the airport of origin to around a maximum of 8,000 ft and to then reduce gently during descent until it matches the ambient air pressure of the destination. A typical cabin altitude, such as the Boeing 767s, is maintained at 6,900 feet when cruising at 39,000 feet. A design goal in newer aircraft is to lower the cabin altitude. For example, the highest internal cabin altitude of the Boeing 787 Dreamliner is equivalent of 6,000 feet, while one of the lowest currently flying is the Bombardier Global Express business jet, which features 4,500 ft when cruising at 41,000 feet. However, the trend for lower cabin altitude on newer aircraft is not universal. Older 747s typically have lower cabin altitude than the newer 777 or A380. The absolute lowest cabin altitude available on an aircraft is found on the Mi Vest SJ30 business jet, which features a sea-level cabin altitude when cruising at 41,000 feet. Keeping the cabin altitude below 8,000 ft generally avoids significant hypoxia, altitude sickness, decompression sickness, and barotrauma, and Federal Aviation Administration regulations in the U.S. mandate that the cabin altitude may not exceed this at the maximum operating altitude of the aircraft under normal operating conditions. This mandatory maximum cabin altitude does not eliminate all physiological problems. Passengers with conditions such as pneumothorax are advised not to fly until fully healed. People suffering from a cold or other infection may still experience pain in the ears and sinuses. Scuba divers flying within the no-fly period after a dive risk decompression sickness, because the accumulated nitrogen in their bodies can form bubbles when exposed to reduced cabin pressure. Before 1996, approximately 6,000 large commercial transport airplanes were type certificated to fly up to 45,000 ft without having to meet high-altitude special conditions. In 1996, the FAA adopted Amendment 25-87, which imposed additional high-altitude cabin pressure specifications for new type aircraft designs. For aircraft certified to operate above 25,000 ft, it must be designed so that occupants will not be exposed to cabin pressure altitudes in excess of 15,000 ft after any probable failure condition in the pressurization system. In the event of a decompression which results from any failure condition not shown to be extremely improbable, the plane must be designed so that occupants will not be exposed to a cabin altitude exceeding 25,000 ft for more than 2 minutes, nor exceeding an altitude of 40,000 ft at any time. In practice, that new Federal Aviation Regulations amendment imposes an operational ceiling of 40,000 ft on the majority of newly designed commercial aircraft. Aircraft manufacturers can apply for a relaxation of this rule if the circumstances warrant it. In 2004, Airbus acquired an FAA exemption to allow the cabin altitude of the A380 to reach 43,000 ft in the event of a decompression incident and to exceed 40,000 ft for 1 minute. This allows the A380 to operate at a higher altitude than other newly designed civilian aircraft. Mechanics. Pressurization is achieved by the design of an airtight fuselage engineered to be pressurized with a source of compressed air and controlled by an environmental control system. The most common source of compressed air for pressurization is bleed air extracted from the compressor stage of a gas turbine engine, from a low or intermediate stage and also from an additional high stage. The exact stage can vary, depending on engine type. By the time the cold outside air has reached the bleed air valves, it is at a very high pressure and has been heated to around 200 degrees Celsius. The control and selection of high or low bleed sources is fully automatic and is governed by the needs of various pneumatic systems at various stages of flight. The part of the bleed air that is directed to the ECS is then expanded and cooled to a suitable temperature by passing it through a heat exchanger and air cycle machine known as the PAC system. In some of the larger airliners, hot trim air can be added downstream of air-conditioned air coming from the packs if it is needed to warm a section of the cabin that is colder than others. At least two engines provide compressed bleed air for all the plane's pneumatic systems, to provide full redundancy. Compressed air is also obtained from the auxiliary power unit, if fitted, in the event of an emergency and for cabin air supply on the ground before the main engines are started. Most modern commercial aircraft today have fully redundant, duplicated electronic controllers for maintaining pressurization along with a manual backup control system. All exhaust air is dumped to atmosphere via an outflow valve, usually at the rear of the fuselage. This valve controls the cabin pressure and also acts as a safety relief valve, in addition to other safety relief valves. If the automatic pressure controllers fail, the pilot can manually control the cabin pressure valve, according to the backup emergency procedure checklist. The automatic controller normally maintains the proper cabin pressure altitude by constantly adjusting the outflow valve position so that the cabin altitude is as low as practical without exceeding the maximum pressure differential limit on the fuselage. The pressure differential varies between aircraft types. Typical values are between 7.8 psi and 9.4 psi. At 39,000 feet, the cabin pressure would be automatically maintained at about 6,900 feet lower than Mexico City, which is about 11.5 psi of atmosphere pressure. Some aircraft, such as the Boeing 787 Dreamliner, have reintroduced electric compressors previously used on piston-engined airliners to provide pressurization. The use of electric compressors increases the electrical generation load on the engines and introduces a number of stages of energy transfer, therefore it is unclear whether this increases the overall efficiency of the aircraft air handling system. It does, however, remove the danger of chemical contamination of the cabin, simplifies engine design, avoids the need to run high-pressure pipework around the aircraft and provides greater design flexibility. Unplanned decompression. Unplanned loss of cabin pressure at altitude is rare but has resulted in a number of fatal accidents. Failures range from sudden, catastrophic loss of airframe integrity to slow leaks or equipment malfunctions that allow cabin pressure to drop undetected to levels that can lead to unconsciousness or severe performance degradation of the aircrew. Any failure of cabin pressurization above 10,000 feet requires an emergency descent to 8,000 feet or the closest to that while maintaining terrain clearance, and the deployment of an oxygen mask for each seat. The oxygen systems have sufficient oxygen for all on board and give the pilots adequate time to descend to below 8,000 ft. Without emergency oxygen, hypoxia may lead to loss of consciousness and a subsequent loss of control of the aircraft. The time of useful consciousness varies according to altitude. As the pressure falls, the cabin air temperature may also plummet to the ambient outside temperature with a danger of hypothermia or frostbite. In jet fighter aircraft, the small size of the cockpit means that any decompression will be very rapid and would not allow the pilot time to put on an oxygen mask. Therefore, fast jet pilots and aircrew are required to wear oxygen masks at all times. History. The aircraft that pioneered pressurized cabin systems include, Packard L'Appariel USA C-11, Engineering Division USD-9A, a modified Airco DH-9A, Junkers Ju-49, Farman F-1000, Kizhevsky BOK-1, Lockheed XC-35, Renada 35, Boeing 307, Lockheed Constellation, Avro Tudor, de Havilland Comet, Tupolev Tu-144 on Concorde. In the late 1910s, attempts were being made to achieve higher and higher altitudes. In 1920, flights well over 37,000 ft were first achieved by test pilot Lieutenant John A. McCready in a Packard L'Appariel copyright LUSA C-11 biplane at McCook Field in Dayton, Ohio. The flight was possible by releasing stored oxygen into the cockpit, which was released directly into an enclosed cabin and not to an oxygen mask, which was developed later. With this system, flights nearing 40,000 ft were possible, but the lack of atmospheric pressure at that altitude caused the pilot's heart to enlarge visibly, and many pilots reported health problems from such high-altitude flights. Some early airliners had oxygen masks for the passengers for routine flights. In 1921, A Wright Dayton USD-9A reconnaissance biplane was modified with the addition of a completely enclosed airtight chamber that could be pressurized with air forced into it by small external turbines. The chamber had a hatch only 22 in diameter that would be sealed by the pilot at 3000 ft. The chamber contained only one instrument, an altimeter, while the conventional cockpit instruments were all mounted outside the chamber, visible through 5 small portholes. The first attempt to operate the aircraft was again made by Lieutenant John A. McCready, who discovered that the turbine was forcing air into the chamber faster than the small release valve provided could release it. As a result, the chamber quickly overpressurized, and the flight was abandoned. A second attempt had to be abandoned when the pilot discovered at 3000 ft that he was too short to close the chamber hatch. The first successful flight was finally made by test pilot Lieutenant Harold Harris, making it the world's first flight by a pressurized aircraft. The first airliner with a pressurized cabin was the Boeing 307 Stratoliner, built in 1938, prior to World War II, though only 10 were produced. The 307's pressure compartment was from the nose of the aircraft to a pressure bulkhead in the aft just forward of the horizontal stabilizer. World War II was a catalyst for aircraft development. Initially, the piston aircraft of World War II, though they often flew at very high altitudes, were not pressurized and relied on oxygen masks. This became impractical with the development of larger bombers where crew were required to move about the cabin, and this led to the first bomber with cabin pressurization, the Boeing B-29 Superfortress. The control system for this was designed by Garrett I Research Manufacturing Company, drawing in part on licensing of patents held by Boeing for the Stratoliner. Post-war piston airliners such as the Lockheed Constellation extended the technology to civilian service. The piston-engined airliners generally relied on electrical compressors to provide pressurized cabin air. Engine supercharging and cabin pressurization enabled planes like the Douglas DC-6, the Douglas DC-7, and the Constellation to have certified service ceilings from 24,000 ft to 28,000 ft. Designing a pressurized fuselage to cope with that altitude range was within the engineering and metallurgical knowledge of that time. The introduction of jet airliners required a significant increase in cruise altitudes to the 30,000 to 41,000 feet range, where jet engines are more fuel efficient. That increase in cruise altitudes required far more rigorous engineering of the fuselage, and in the beginning not all the engineering problems were fully understood. The World unregistered trademark S first commercial jet airliner was the British de Havilland Comet, designed with a service ceiling of 36,000 ft. It was the first time that a large diameter, pressurized fuselage with windows had been built and flown at this altitude. Initially, the design was very successful, but 2 catastrophic airframe failures in 1954 resulting in the total loss of the aircraft, passengers and crew grounded what was then the entire world jet airliner fleet. Extensive investigation and groundbreaking engineering analysis of the wreckage led to a number of very significant engineering advances that solved the basic problems of pressurized fuselage design at altitude. The critical problem proved to be a combination of an inadequate understanding of the effect of progressive metal fatigue as the fuselage undergoes repeated stress cycles, coupled with a misunderstanding of how aircraft skin stresses are redistributed around openings in the fuselage such as windows and rivet holes. The critical engineering principles concerning metal fatigue learned from the Comet 1 program were applied directly to the design of the Boeing 707 and all subsequent jet airliners. One immediately noticeable legacy of the Comet disasters is the oval windows on every jet airliner. The metal fatigue cracks that destroyed the Comets were initiated by the small radius corners on the Comet 1 unregistered trademark S almost square windows. The Comet fuselage was redesigned and the Comet 4 went on to become a successful airliner, pioneering the first transatlantic jet service, but the program never really recovered from these disasters and was overtaken by the Boeing 707. Concorde had to deal with unusually high pressure differentials because it flew at unusually high altitude, and maintained a cabin altitude of 6,000 ft. This made the aircraft significantly heavier and contributed to the high cost of a flight. The Concorde also had smaller cabin windows than most other commercial passenger aircraft in order to slow the rate of decompression if a window failed. The high cruising altitude also required the use of high-pressure oxygen and demand valves at the emergency masks, unlike the continuous flow masks used in conventional airliners. The designed operating cabin altitude for new aircraft is falling, and this is expected to reduce any remaining physiological problems. See also, aerotoxic syndrome, air cycle machine, atmosphere, compressed air, fume event, rarefaction, spacesuit, time of useful consciousness. Footnotes. General references, Seymour L. Chapin. Garrett and Pressurized Flight, a business built on thin air. Pacific Historical Review 35, 329 €43 doi, 10.2307/3636792 Seymour L. Chapin. Patent Interferences in the History of Technology, a High-Flying Example. Technology and Culture 12, 414 €46 doi, 10.2307/3102997. JSTORA 3102997 A. Cornelis, Diana G. Splendid Vision, Unswerving Purpose. Developing Air Power for the United States Air Force During the First Century of Powered Flight. Wright-Patterson Air Force Base, Ohio, U.S. Air Force Publications, 2002. ISBN 0-16-067599-5 ppA 128 to 129. Portions from the United States Naval Flight Surgeon's Manual, CNN, 121 Dead in Greek Air Crash.